When you build a complex system, you hit a wall quickly. Optimizing one priority almost always degrades another. If you maximize performance, you sacrifice privacy. Every decision creates an invisible tension where competing forces pull against each other. Over the next 6 minutes, we are going to map exactly how to measure this triadic balance. We will calculate it mathematically using the harmony index, and then visualize it using the Marshall triangle. To do this, you do not need a massive dataset. You only need 3 raw data points representing your competing priorities. From those 3 numbers, we can generate a continuous, readable visual map of your entire system. Navigating these systems requires moving past a single metric of success. This process allows you to map competing priorities as a continuous field, revealing exactly how a choice in one area impacts the stability of the others. Step 1 is identifying your axes. In the Quetra reference model, we use 3 specific priorities: privacy, performance, and personalization. We call these the PPP axes. Look at your current system state and pull the raw numeric scores for each of those 3 axes. Keep them close by. Now we apply normalization. Because your raw scores might be measured on completely different scales, we have to convert them into proportionate fractions so that all 3 sum up to exactly 1.0. The math is straightforward. You take each individual axis score and divide it by the total sum of all 3 axes. Let's plug in real numbers. If your raw vector is 40 for privacy, 20 for performance, and 60 for personalization, your total is 120. Divide each by 120 and your normalized vector becomes 0.33, 0.16, and 0.50. Stop here and run a quick check. Add your 3 new decimal values together. They must equal exactly 1.0. If they do, your math is correct. Normalization strips away arbitrary, confusing scoring scales. It places vastly different system states onto a single, equal geometric playing field, so we can make true apples-to-apples comparisons. This diagram shows the Marshall triangle. Right in the dead center is the white point, which represents your system's target equilibrium center. By default, this white point is a perfectly symmetrical split, 0.33 on all 3 axes. But depending on your needs, you can calibrate your own custom white point to define what balance means for your specific situation. Once we have that target, we calculate tension. We measure the Euclidean distance to find exactly how far your current normalized vector has drifted away from your white point. We then convert that tension distance into a scalar score called the harmony index. You calculate this by taking 1 minus the tension divided by 0.8165. The harmony index is restricted to mechanical state classification. It remains an objective indicator of system alignment, separate from any measure of user achievement, rank, or personal worth. This technical tension value translates directly into interface status labels. It indicates mathematically whether a system state is currently at your center or if it is drifting. The harmony index functions as an objective indicator of systemic displacement. It reveals when a system is out of alignment, providing a metric for adjustment without imposing a subjective judgment on the state itself. This image displays the full Marshall triangle. It serves as a continuous visual map for the data we just calculated. Notice the framework's unique rule. The primary sources are anchored at the edge midpoints rather than the vertices. Red marks the privacy axis, green is performance, and blue is personalization. Secondary, blended states emerge at the vertices. These corners, yellow, cyan, and magenta, are locations where 2 primary axes exert equal influence while the third is minimized. This comparison shows how the geometry responds visually when the system's underlying state shifts. Look at the balanced default state in Panel B and compare it to the state in Panel C. Panel C has a heavy privacy emphasis, causing the visual center of gravity to pull drastically toward the red axis. When a system experiences high tension, it creates a dynamic shift. The white point of neutral recombination physically pulls away from the geometric center and moves toward the dominant priority. This specific geometric visualization avoids collapsing data into a single, confusing number. It makes complex multi-objective trade-offs instantly legible to the human eye as continuous, shifting gradients. Let's review the entire pipeline. As you move the UI sliders, the system calculates the tension. That tension updates the scalar harmony index, which then dynamically shifts the color field on the Marshall triangle in real time. You have successfully taken abstract, competing priorities and transformed them into a precise mathematical formula and a readable visual map. Your next step is to experiment with setting a custom white point. Doing this allows the system's definition of balance to become personalized to your exact requirements. Having a formal way to resolve value conflicts allows us to build durable systems, architectures that can hold competing goods in a stable, dynamic equilibrium.